One of the most interesting things about physics is that sometimes the things we learn first, the things that seem most obvious, turn out to be not quite right, and gravity is a perfect example of this. Now, when you were in school, somebody told you that gravity is a force. Newton told us that, right? There's this force between masses. It goes as 1 over the distance squared. Very nice, very simple. And it works. It works beautifully for calculating how the planets move, how apples fall from trees, all of that. But here's the thing. It's not actually a force, at least not in the way we think about forces. Let me tell you what I mean. When we talk about forces in physics, we usually mean something that pushes or pulls on an object and makes it accelerate. If I push this book across the table, that's a force. If I pull on a rope, that's a force. These are real forces, electromagnetic forces actually, coming from the interaction between atoms in my hand and atoms in the book. But gravity is something else entirely. Einstein figured this out, and it's one of the most beautiful ideas in all of physics. He said, and this is remarkable, he said that what we call gravity isn't a force at all. It's the shape of space and time. Now that sounds crazy, doesn't it? How can the shape of something make things move? But let me explain it to you, and I think you'll see why this is such a profound idea. First, we have to talk about something called space-time. You see, space and time aren't really separate things. They're part of one thing, one fabric, if you like. We live in a four-dimensional world, 3 dimensions of space and 1 of time. And this fabric, this space-time, can be curved, it can be bent, it can be warped. Now, what does it mean for space-time to be curved? This is hard to visualize because we're stuck in 3 dimensions, trying to imagine a 4-dimensional thing being curved. So let me give you an analogy. Imagine you have a nice flat rubber sheet stretched out. That's like flat space-time. Now, if you put a bowling ball in the middle of that sheet, what happens? The sheet curves down around the ball. It makes a dip, a depression in the sheet. That's what massive objects do to space-time. The Earth, the sun, every massive object, they curve space-time around them. And the more mass you have, the more you curve it. The sun curves space-time more than the Earth. A black hole curves it so much that the curvature becomes extreme. Now here's the key point, and this is where it gets really interesting. When you have this curved space-time, objects don't need a force to make them move the way they do. They're just doing what comes naturally. They're moving along the straightest possible path in this curved geometry. What does that mean? Well, on a flat surface, the straightest path between 2 points is a straight line. That's obvious. But on a curved surface, like the surface of the Earth, the straightest path between 2 points is actually curved. If you fly from New York to Tokyo, you don't fly in what looks like a straight line on a flat map. You fly along what's called a great circle route. It's curved, but it's the straightest path you can take on the curved surface of the Earth. In curved space-time, objects move along what we call geodesics. A geodesic is the straightest possible path in curved space-time. And here's the beautiful part. This explains everything we see as gravity without ever invoking a force. Think about the Earth orbiting the sun. Newton would say there's a gravitational force pulling the Earth toward the sun, and that force makes the Earth move in a curved path, an ellipse. But Einstein says no, no, no. The sun curves space-time around it, and the Earth is just moving along a geodesic, a straight path in that curved space-time. The path looks curved to us in 3-dimensional space, but in 4-dimensional space-time, it's the straightest possible path. There's no force pulling the Earth toward the sun. The Earth is just doing what objects do naturally in curved space-time. It's following a geodesic. It's like rolling a marble on that rubber sheet with the bowling ball in the middle. The marble doesn't go straight across in a Euclidean sense. It curves around the depression. But from the marble's point of view, from the point of view of something moving through that curved geometry, it's going straight. Now you might say, wait a minute. When I drop this book, it falls down. That feels like a force, and you'd be right to be puzzled by that. Let me explain. When you're holding the book, you're preventing it from doing what it wants to do naturally, which is to follow a geodesic in the curved space-time around the Earth. The Earth curves space-time, and the natural path for the book, its geodesic, is to move toward the center of the Earth. But you're holding it up. You're applying a force to prevent it from following its natural path. When you let go, the book isn't having a force applied to it that makes it fall. It's just following its natural path. It's geodesic through curved space-time. What feels like falling to you is actually the book moving along the straightest possible path in curved space-time. And here's something that will really blow your mind. When you're standing on the ground, you're the one experiencing a force. You're not in free fall. You're not following a geodesic. The ground is pushing up on you, and that's an electromagnetic force from the atoms in the ground pushing against the atoms in your feet. That force is preventing you from following your natural geodesic, which would take you toward the center of the Earth. So when you're standing still on the ground, you're actually accelerating in the framework of general relativity. You're being accelerated upward by the ground. And when an object is falling, it's not accelerating in the general relativistic sense. It's in free fall, moving along a geodesic, feeling no force at all. Now, if you've been paying attention, you might ask a very good question. You might say, but wait, all objects fall at the same rate, regardless of their mass. How does curved space-time explain that? And that's exactly the right question to ask. This was one of the key insights that led Einstein to his theory. Galileo figured out hundreds of years ago that if you drop a heavy object and a light object from the same height, they hit the ground at the same time. Ignoring air resistance, a bowling ball and a feather fall at the same rate. Newton's theory could explain this, but it had to assume that inertial mass and gravitational mass were exactly equal, which was a bit of a coincidence. But in Einstein's picture, it's not a coincidence at all. It's inevitable, because gravity isn't a force acting on mass. It's the curvature of space-time itself. Every object, regardless of its mass, follows geodesics in space-time. A massive object and a light object both follow the same geodesic if they start from the same place with the same velocity. They have to fall at the same rate because they're both just following the geometry of space-time. This is called the equivalence principle, and it's one of the deepest ideas in physics. It says that being in a gravitational field is exactly equivalent to being in an accelerating reference frame. If you're in a closed elevator with no windows, there's no experiment you can do to tell the difference between sitting still on Earth and accelerating through space at 9.8 meters per second squared. Now, let me tell you about some evidence for this picture, because it's all very well to have a beautiful theory, but physics is about nature, and we have to check if our theories match what nature actually does. One of the first tests of general relativity was the bending of starlight. Einstein predicted that because massive objects curve space-time, light should also follow curved paths when it passes near a massive object. During a solar eclipse in 1919, astronomers measured the positions of stars that appeared near the sun in the sky. And sure enough, the light from those stars was bent as it passed near the sun, exactly as Einstein predicted. Now you might think, well, maybe light is being pulled by gravity as a force. But light has no mass, so in Newton's theory, it shouldn't be affected by gravity at all. The fact that light follows curved paths in curved space-time is a direct confirmation that gravity is about the geometry of space-time, not about forces between masses. Another beautiful piece of evidence comes from something called gravitational time dilation. Because space-time is curved near massive objects, time actually runs at different rates at different positions in a gravitational field. Clocks that are deeper in a gravitational well, closer to a massive object, run slower than clocks that are farther away. This isn't just theory. We've measured it. We've put atomic clocks at different altitudes and confirmed that the clock at higher altitude runs faster. And this effect is actually important for GPS satellites. If we didn't correct for gravitational time dilation, GPS wouldn't work. Your position would be off by kilometers after just a few hours. And then there are gravitational waves. If space-time can be curved, it can also ripple. When massive objects move, like two black holes orbiting each other and eventually colliding, they create ripples in space-time that propagate outward at the speed of light. These are gravitational waves, and we've detected them. In 2015, the LIGO experiment detected gravitational waves from two black holes merging more than 1 billion light years away. These ripples in space-time passed through the Earth, causing tiny changes in the distances between objects. Changes so small that they're thousands of times smaller than the size of a proton, but we could measure them. This is direct evidence that space-time is a real physical thing that can be warped and can carry waves. It's not just a mathematical abstraction, it's real. Now, I want to talk about a subtlety that comes up when people learn about this. Sometimes people ask, if gravity isn't a force, why do we still call it a force? Why do we talk about the force of gravity in everyday language? Well, that's a good question. The answer is that for most practical purposes, it doesn't matter. If you're calculating how fast a ball falls or what orbit to put a satellite in, Newton's equations work perfectly well. You can treat gravity as a force and you'll get the right answer. But fundamentally, at a deep level, gravity is different from other forces. The electromagnetic force, the strong nuclear force, the weak nuclear force, these are real forces mediated by particles. Electromagnetism is mediated by photons, the strong force by gluons, and so on. But gravity is the curvature of space-time itself. It's not mediated by particles in the same way, though physicists are still trying to understand how to describe gravity at the quantum level. You might also wonder, how do we know which picture is right? Is gravity a force, or is it curved space-time? Well, here's the thing. Both pictures can give you correct predictions in many situations, but Einstein's picture of curved space-time gives you correct predictions in situations where Newton's picture fails. For example, Mercury's orbit. Mercury is the closest planet to the Sun, and its orbit does something funny. The point of closest approach to the Sun, the perihelion, slowly rotates over time. Most of this rotation can be explained by the gravitational pull of the other planets, but there was a tiny discrepancy that Newton's theory couldn't explain. Einstein's theory explained it perfectly. The strong curvature of space-time near the Sun causes this extra precession. Or think about black holes. In Newton's theory, you could imagine an object so massive and so compact that not even light could escape from it, but you'd still think of it as having a gravitational force. In Einstein's theory, a black hole is a region where space-time is curved so much that geodesics, the straight paths, lead inward and never come back out. It's not that there's a force pulling things in. It's that the geometry of space-time itself is such that all paths lead inward. Even light, following its geodesic, can't escape. Now, I should tell you something important. While Einstein's picture is more accurate and more fundamental, it's also more complicated mathematically. The equations of general relativity, Einstein's field equations, are complicated. They're nonlinear, partial differential equations, and solving them exactly is very difficult. We can only solve them exactly in very simple situations, like the space-time around a perfectly spherical, non-rotating mass. For most practical problems, we have to make approximations, and often the best approximation is to just use Newton's theory and treat gravity as a force. Engineers designing satellites don't usually need general relativity. Newton's laws work fine. But for GPS satellites, for understanding black holes, for cosmology and the evolution of the universe, for these, you need Einstein. Let me tell you one more thing that I find absolutely fascinating. When Einstein first developed general relativity, he realized that his equations didn't just describe how matter curves space-time. They also described how the curvature of space-time tells matter how to move. There's a beautiful interplay. As John Wheeler, one of the great physicists of the 20th century, put it, space-time tells matter how to move. Matter tells space-time how to curve. This is fundamentally different from Newton's picture, where space is just an unchanging stage on which matter moves around, with forces acting between objects. In Einstein's picture, space-time is a dynamical thing. It responds to matter and energy respond to it. And here's something that's still an open question in physics. We know how to describe gravity as curved space-time in general relativity. We know how to describe the other forces, electromagnetism, the strong force, the weak force, using quantum mechanics and quantum field theory. But we don't yet know how to fully reconcile these two pictures. We don't have a complete theory of quantum gravity. This is one of the big unsolved problems in physics. How do you describe gravity at the quantum level? Some people are working on string theory, some on loop quantum gravity, some on other approaches. But we don't have the answer yet. Now, after all this, you might be wondering, what should you take away from this? What's the key point? The key point is this. What we call gravity isn't a force in the traditional sense. It's not something pulling on you. It's the curvature of space-time caused by mass and energy. When you see an apple fall from a tree, it's not being pulled down by a force. It's following the straightest possible path through the curved space-time around the Earth. This is one of the most beautiful ideas in all of physics. It tells us that geometry, something that seems abstract and mathematical, is actually deeply connected to the physical world. The shape of space-time determines how objects move, and massive objects determine the shape of space-time. It's a radically different way of thinking about gravity than Newton's picture, and it takes some getting used to. But once you see it, once you really understand it, it's incredibly elegant. Nature doesn't need to have mysterious forces acting across vast distances. She just needs curved space-time, and everything else follows. And that, to me, is what makes physics beautiful. You start with what seems like a simple observation. Things fall down. And when you really dig into it, when you really try to understand what's going on, you discover something profound about the nature of space and time themselves. So the next time someone tells you that gravity is a force, you can tell them, well, yes, that's a useful way to think about it for many purposes. But fundamentally, gravity is something much more interesting. It's geometry. It's the curvature of the very fabric of space-time. And that's far more remarkable than any force could ever be.